You know that feeling, right? You're driving along, maybe minding your own business, just cruising, and then bam.
Uh-oh.
Yeah, that sudden, kind of unsettling dashboard light flicks on.
Yeah.
Or maybe your car starts making some weird new sound from under the hood.
Oh, yeah. Could be anything. A pinging, maybe a deep thumping noise, or sometimes like a high-pitched squeal.
Exactly. And whatever it is, you're instantly like, okay, what is my car trying to tell me? And maybe even more pressing, how much is this going to cost me?
It's that universal moment, isn't it? That automotive mystery where the language of your vehicle just feels totally foreign, leaves most of us feeling pretty powerless, actually.
Totally powerless. And that's precisely why we're here today. Welcome to the deep dive. Think of us as your shortcut to actually understanding what's going on with your car.
Yeah, and this isn't just, some hardcore class for mechanics in training.
No, not at all. This is really tailor-made for you.
Yeah.
You, the curious learner, the informed car owner who just wants to feel, well, more empowered and maybe a little less anxious when it comes to your wheels.
Right. So today we're diving deep, really getting into the weeds of auto maintenance and light repair.
And we're doing it through the lens of a really key industry benchmark, the ASE G1 certification.
Yep. We've pulled insights straight from a pretty comprehensive study guide. It's packed with details on, well, pretty much every major vehicle system.
Plus, we found this surprising little ad in there about something that gets overlooked a lot, but
Yep.
it's absolutely crucial.
The parts themselves.
Exactly. So our mission for you today, we want to transform that common confusion into, hopefully, crystal clear clarity.
Giving you the power of knowledge, and maybe, just maybe, a lot less anxiety the next time one of those dashboard lights decides to crash the party.
Okay, let's unpack this then. We're talking ASE G1 certification. Now, for someone like me, who isn't planning on becoming a certified mechanic anytime soon, why should this even be on my radar? What exactly is it, and why does it matter so much?
That's a really fundamental question because the why here, it really boils down to trust. Trust and quality. So ASE stands for the National Automotive Service Excellence. It's actually a nonprofit, totally independent organization started way back in 1972.
Wow, that long ago.
Yeah. Think of it like the ultimate quality assurance program for the whole auto repair industry. Their main job, their core mission, is setting up and maintaining really tough standards for automotive professionals.
So making sure the person working on your car actually knows what they're doing.
Precisely. It ensures that when you take your car in for service, the technician touching it really truly knows their stuff. They're not just guessing.
Okay, so it's about vetting them, making sure
Yes.
they're tested.
Exactly. ASE certifies technicians across, get this, more than 40 different specialist areas. The scale is actually pretty impressive. There are over 400,000 certified techs across the country.
400,000, wow.
Yeah. And the reason these certifications exist, it's kind of multifaceted. On one hand, it definitely promotes excellence within the field itself, right? It pushes technicians to keep learning, keep upgrading their skills. This verifies their knowledge, gives them a credential that often leads to better pay, better jobs. But for you, the car owner, the public, the biggest benefit is just this huge boost in consumer confidence.
Okay, so I can trust the work more.
Right. It means you can have way more trust and assurance in the quality of the repair work being done on your vehicle. You see that ASE patch? It means something.
And the G1 certification specifically, what does that one focus on?
Right, G1. That one zeroes in on auto maintenance and light repair. It's kind of considered the foundational knowledge, the basics of car care.
Fundamentals.
Exactly. So while, yeah, it's often a stepping stone for new mechanics just starting out, the actual information covered by G1 standards, it's incredibly valuable for any car owner who just wants to understand the core workings of their vehicle.
So it helps me speak the same language as my mechanic.
That's a perfect way to put it. It helps you speak their language, understand their diagnoses better, and just feel way more confident about the repair decisions you end up making. You're not just nodding along anymore.
That makes total sense. Knowing the standard helps you know what quality looks like
Right.
and who's actually qualifies. And speaking of standards, how do they even measure this knowledge? If we decode the test itself, how does ASE figure out if someone really gets these fundamentals? What's the G1 test actually look like?
So the G1 test itself, it's typically somewhere between 80 and 90 multiple choice questions.
Okay.
And it's all computer-based now, a CBT, which is nice because technicians get their score immediately. They know right away if they passed or failed.
Instant feedback.
Yep. But the really insightful part, I think, especially from a learner's perspective, isn't just the format, it's the types of questions they ask. because they really reflect the kind of diagnostic thinking that even, an informed car owner can really benefit from developing.
Ah, okay. So it's not just memorizing parts. What kind of thinking do these questions actually demand?
Right. It goes beyond just simple recall. They use several distinct question types to measure different things. Knowledge, reasoning.
Yep.
First, you've got your direct completion questions. These are pretty straightforward. Factual recall, like the common cause of brake pedal pulsation is. You just need to know the answer.
Huh.
Warped rotors, usually.
Got it. Basic facts.
Foundational knowledge, exactly. Then they have most likely, least likely questions. Now, these require you to identify the most probable or maybe the least probable cause or solution for a given scenario.
Like troubleshooting.
Pretty much. For example, when a cylinder head is warped, which repair is most likely needed? You have to weigh the options. Is it resurfacing, replacement, something else? It forces you to think about efficiency, effectiveness, just like in a real shop.
Okay, that makes sense.
What else? Then you get the technician A and B questions. These are really good for testing practical application, I think. They give you two statements from hypothetical texts, technician A and technician B.
Right, I've seen those.
Yeah, and you have to figure out which one is correct. Or maybe both are, or maybe neither. It really tests your diagnostic reasoning, your ability to compare different approaches, or maybe spot common mistakes.
Can you give an example?
Sure. Like, Technician A says that when pressure testing a radiator cap, a special adapter is needed. Technician B says the best way to check thermostat operation is while it is in the engine. Who's right?
I'd guess B, because the thermostat needs heat to open.
You got it. Technician B is correct. Because a thermostat works based on temperature, right? So you need to see it in its actual operating environment in the engine. These questions challenge assumptions, make you think deeper about why things are done a certain way.
I like those. What's the last type?
The last main type is except T-naught questions. These kind of flip things around. They give you a list of mostly true statements and ask you to find the one that's incorrect.
The outlier.
Exactly. Like, all of the following are true regarding torsion bars except TVD,
Yeah.
and you have to pick the one false statement. It forces you to really think critically about what you know by identifying what doesn't fit.
Wow. So yeah, definitely not just rote memorization. It's about applying knowledge, understanding how things connect, thinking like a detective almost. Really tests that critical thinking.
Precisely. And understanding how this knowledge gets tested, it helps you appreciate the depth that's required, right?
But,
And how information needs to be organized logically for finding problems and solving them.
yeah.
It's about connecting those dots, taking individual facts, and building a coherent picture of how the car works, and more importantly, how to figure out what's wrong when it doesn't.
So for me, the listener, it means I'm learning to think more like a pro, not just rattling off car parts.
That's the goal. That kind of critical thinking, honestly, it can save you a ton of time, money, and just sheer frustration down the road.
Okay, this is where it gets really interesting, I think. Let's crack open this study guide, metaphorically, and take a bit of a whirlwind tour through the key systems inside your car.
Let's do it.
Because even if you're not aiming to become a certified mechanic, just understanding these basics, it can save you so many headaches. It helps you ask better questions at the shop and just makes you a more informed, confident car owner overall.
Absolutely. It's about giving you the tools to kind of speak car, right? And maybe even spot issues before they turn into huge, expensive problems.
Exactly. So where do we start?
We'll break down the main content areas from the G1 test. We'll hit the key insights, common problems for each one, often looking at it like a technician would, but always keeping in mind what you, the driver, really needs to know. #####. Engine systems. 34% of G1 test 19 questions. All right, first up, engine systems. This is the biggest chunk of the G1 test, about 34%, roughly 19 questions.
Makes sense. It's the heart of the car, right?
Exactly. It's the power source. So naturally, it's where a huge number of potential problems can pop up.
So, okay, you're faced with a car that's just not running right. How does a mechanic even begin to figure out what's wrong? It seems overwhelming, like finding a needle in a haystack sometimes.
It can feel that way for sure, but there's a process. For a good mechanic, the starting point is always the customer complaint. What did you notice? What did it sound like, feel like?
The first clue?
The very first clue. It guides everything. So the tech verifies that symptom first. Let's say you report a rough idle. They confirm it. Then they check for related stuff, any technical service bulletins, TSBs, or maybe recalls for that model.
Okay.
Next comes a really thorough visual inspection. Then they'll likely hook up a scan tool, read any trouble codes the car's computer has stored.
The check engine light codes.
Right. Those point them in the right direction. Then they do more specific tests based on those codes and symptoms. And the final, absolutely crucial step, verifying the repair, making sure the problem is actually fixed before giving it back to you. It's systematic detective work.
That diagnostic flow makes sense. So what are some of the most common engine problems that might send someone like me running to the mechanic?
Well, leaks are a big category, and they range from just annoying to seriously dangerous. Fuel leaks, for instance, are incredibly serious.
Fire hazard, right.
Huge fire hazard. You might notice a really strong gasoline smell, maybe even see drips under the car. Causes can be damaged fuel lines, loose fittings, maybe just old, deteriorated O-rings. Inspection means using your nose, looking carefully, sometimes pressure testing the system. Needs immediate attention, no question.
Okay, fuel leaks, check. What else leaks?
Then you have oil leaks. These can come from gasket that have gotten hard and brittle, maybe loose bolts or fasteners, or sometimes, interestingly, excessive pressure building up inside the engine's crankcase.
Pressure. How does that happen?
It's often due to problems with the PCV system, that's the positive crankcase ventilation system. Think of it like the engine's breathing system. It needs to vent pressure. If the PCV valve gets clogged or stuck, pressure builds up and can force oil out past seals and gaskets.
Ah, okay. So how would I spot an oil leak?
You might see dark spots on your driveway where you park, or maybe smell burning oil if it's dripping onto hot exhaust parts. Checking your oil level on the dipstick regularly is key, too. If it's dropping, the oil's going somewhere.
Right. And the third common leak?
Coolant leaks, another big one. These often come from loose hose clamps, worn-out hoses, or maybe cracked components like the radiator itself or the water pump.
What should I look for?
Puddles of colorful liquid under your car, usually bright green, maybe orange, pink, or blue, depending on the type. But the real telltale sign is your engine temperature gauge climbing way up into the red. Overheating.
Bad.
It's very bad. Overheating from a coolant leak can cause massive, expensive engine damage very quickly. Things like warped cylinder heads. You see that temp gauge rising, pull over safely as soon as you can.
Good advice. Okay, so beyond leaks, you mentioned sounds. My car definitely talks sometimes. What noises should I be listening for from the engine? What are the distress signals?
Listening is huge. Engine noises are like direct messages, and different sounds point to very specific problems. Paying attention can give you a massive head start.
Okay, like what?
Bearing noise. This is usually a deep, dull, heavy knocking sound, almost like a rhythmic thump coming from deep inside the engine. It often gets louder or faster as you increase engine RPMs.
And that
Usually indicates serious wear in the engine's main bearings or connecting rod bearings. Not good news. Needs immediate professional diagnosis.
Okay. Deep, dull knock. What else?
Spark knock. You might hear it called detonation or pinging. It sounds like a metallic pinging, or maybe like marbles rattling around in a coffee can. It's most noticeable when you accelerate.
Is that serious?
Extremely serious. It happens when the air-fuel mixture ignites too early, kind of like a small explosion happening at the wrong time. It creates huge pressure spikes inside the cylinders that can destroy pistons really quickly.
Wow. What causes that?
Could be a few things. Running too lean a fuel mixture, heavy carbon buildup inside the engine, using the wrong octane fuel, or problems with ignition timing. Needs immediate attention. Don't ignore pinging.
Got it. Metallic pinging's bad, Dan. Any other distinct sounds?
Yeah, piston pin noise. This is usually a sharper, lighter, metallic tapping sound. Often it's more noticeable when the engine is cold and might quiet down a bit as it warms up. Related to wear between the piston and the connecting rod.
Okay, and one more.
Hydraulic lifter noise. This is typically a rapid ticking sound, like a sewing machine almost. Often related to your oil level being low, or maybe dirty oil or other issues in the valve train, the parts that open and close your engine's valves.
Can that be fixed easily?
Sometimes it's as simple as an oil change or topping off the oil, but it still indicates something needs looking at. And it really underscores why regular on-time oil changes are just absolutely critical for preventing a lot of these oil-related noises and wear.
Right. That brings us neatly to preventative care. We hear about oil changes all the time. What are the absolute must-do maintenance things for the engine that every car owner should really know about?
Yeah, you're hitting the core of keeping that engine happy and living a long life. Oil and filter changes, number one, non-negotiable.
Why exactly is oil so important?
Engine oil does three main jobs. It lubricates all those fast-moving metal parts to reduce friction and wear. It helps cool the engine by carrying heat away, and it cleans suspending dirt and contaminants. But over time, it breaks down, gets dirty.
So change it regularly and check the level.
Absolutely. Know how to check your oil on the dipstick, look for the ADD and full marks, make sure the level is in between, wipe it, dip it, read it. Simple. And also, a small but important point, dispose of used oil properly. Don't just dump it. Most auto parts stores or repair shops will take it.
Good tip. Okay, oil changes. What else is crucial?
The cooling system. We talked about leaks, but general maintenance is key. Its job is regulating engine temperature, keeping it in that optimal range. Key parts are the radiator, the water pump, and the thermostat.
What does the thermostat actually do?
The thermostat's function is super important. When you first start the car cold, it stays closed, blocking coolant flow to the radiator. This lets the engine warm up really quickly to its ideal operating temperature. Faster warm-up means better efficiency, lower emissions.
Hey.
Then, once the engine reaches that temperature, the thermostat opens up, allowing coolant to flow through the radiator to get cooled off, maintaining that steady, optimal temperature.
So if it gets stuck.
If it sticks closed, the engine overheats. If it sticks open, the engine might never reach its proper operating temperature, which hurts fuel economy and performance and can sometimes trigger a check engine light.
Got it. Thermostat is key. Anything else on the basic maintenance list?
Belts. Specifically, the serpentine belt on most modern cars. It's usually one long, winding belt that drives multiple accessories. Your alternator, power steering pump, air conditioning compressor, maybe the water pump too.
One belt does all that.
Yep. Which is why checking it is important.
Yeah.
You need to check its tension. It shouldn't be too loose or too tight, and visually inspect it for cracks, fraying, glazing, or any missing chunks or ribs.
What happens if it breaks?
If it snaps, you lose power to all those accessories instantly. No power steering assist, no battery charging from the alternator, no AC. You could overheat if it drives the water pump. Basically, you're probably stranded. So regular checks are smart.
Definitely. Okay, we've covered the mechanical bits. But cars today are like computers on wheels, right? What about the electronic brain, all those sensors feeding it information? What do we need to know about that complex nervous system?
Yeah, nervous system's a great analogy. Think of your car's critical sensors as its senses. They're constantly monitoring everything.
Like what? Give me some key examples.
Okay, the oxygen O2 sensor. It sits in the exhaust and measures how much oxygen is left after combustion. That tells the engine computer if the fuel mixture is too rich or too lean, so it can adjust for best fuel efficiency and lowest emissions. Crucial sensor.
Okay, O2 sensor. What else?
Then you have the camshaft position, CMP, and crankshaft position, CKP sensors. These tell the computer the exact rotational position of the engine's camshaft and crankshaft. This info is absolutely vital for timing the ignition spark and the fuel injection perfectly. If these fail, the car might not start at all.
Wow. Okay, vital sensors. Keep going.
The knock sensor. Remember that dangerous spark knock or pinging we talked about?
Yeah, the marbles in a can sound.
Exactly. The knock sensor is like the engine's ear, listening specifically for that sound. If it detects knock, it immediately signals the engine control module, the ECM, the brain, to adjust the ignition timing, usually retarding it slightly, to stop the knock and prevent damage. It's like an engine bodyguard.
Cool. What else?
Mass airflow, MAF sensor. This measures the actual mass or amount of air entering the engine. The ECM needs this info to calculate precisely how much fuel to inject to get the ideal air-fuel ratio for different conditions.
Makes sense. Air in, fuel in proportion.
Right. The throttle position, TPS sensor. This one simply tells the ECM how far you've pressed the accelerator pedal. Are you idling? Cruising, flooring it? That helps determine fuel delivery and transmission shifting.
Okay, one more.
Let's do the vehicle speed sensor, VSS. This monitors how fast the wheels are turning, or the vehicle speed. This data is used by the transmission for shifting, by the cruise control system, and also by the anti-lock braking system, the ABS.
So all these sensors are constantly talking to the car's brain.
Constantly feeding data to the ECM. And the ECM uses all that input to make millions of tiny adjustments every second to keep the engine running efficiently, powerfully, and cleanly. It's an incredibly complex, real-time balancing act.
So if one of these sensors goes bad or gives faulty information, that's usually when you get that dreaded check engine light, isn't it?
Exactly right. That light coming on means the engine's control system has detected a problem, something outside of its normal operating parameters, and it has stored a diagnostic trouble code, or DTC, in its memory.
A code for the specific problem.
Well, it points to the area of the problem. Modern cars use the On-Board Diagnostics 2, OBD2 system. When a problem occurs that could affect emissions or engine performance, the system generates a specific code. like P0301 for a misfire in cylinder 1, or P0420 for a catalytic converter issue.
How do you read the codes?
A technician uses a scan tool, plugs it into a standard port under your dashboard, and reads the stored codes. Now, the code doesn't automatically tell you, replace this part. It tells the technician which system or circuit is having trouble, guiding their diagnosis. So P0301 means check cylinder 1, could be the spark plug, the ignition coil, the fuel injector, or even a mechanical issue.
Okay, so the light isn't a panic button. It's more like a, hey, check this out signal.
Precisely. Knowing that the light means a code has been set, and that code is a starting point for a professional diagnosis, can definitely lower the stress level a bit.
Definitely helps. Now, what about spark plugs? I know they're key for actually igniting the fuel. Can they tell you anything beyond just time for new ones?
Oh, absolutely. Spark plugs are like little windows into the combustion chamber. A good mechanic can read a used spark plug and get a ton of information about what's happening inside that cylinder. They offer direct visual clues.
Really? What kind of clues?
Okay, let's say a plug has gap bridged. That means deposits, usually carbon or oil, have built up between the two electrodes, shorting out the spark. That points to maybe excessive oil consumption or a rich fuel mixture.
Okay.
An oil-fouled plug looks literally wet and black with oily deposits. That's a clear sign. Oil is getting into the combustion chamber where it shouldn't be. Could be worn piston rings, valve seals, something like that.
Right. Burning oil.
Exactly. A carbon-fouled plug is covered in dry, black, sooty deposits. That usually points to running too rich a fuel mixture, maybe a weak spark or excessive idling.
Okay, black and sooty, too much fuel.
Generally. An overheating plug will have a white, maybe blistered-looking insulator around the center electrode. That tells you the plug is running too hot for the conditions. Could be the wrong heat range plug for the engine, maybe ignition timing is too advanced, or the engine is running lean.
White means too hot.
Got it. And then you can get signs of pre-ignition or severe detonation. The electrodes might look melted, blistered, or even broken. That indicates extreme temperatures and pressures in the cylinder, often caused by things like glowing carbon deposits, the wrong fuel, or serious timing issues. That's really bad news.
Wow. So just by looking at those little plugs, a mechanic can get a really specific idea of the engine's internal health.
It's a fantastic diagnostic tool. It guides them towards the root cause without having to tear the whole engine apart first. Huge time saver, very informative.
It really is fascinating how much info is packed into such a small part.
Okay, let's shift slightly to emissions and fuel systems. These are obviously crucial for performance, fuel economy, and, the environment.
Absolutely vital on all fronts. Let's start with the PCV system again, positive crankcase ventilation. We mentioned it regarding oil leaks. Its main job is to take those normal combustion blow-by gases that sneak past the piston rings into the crankcase and route them back into the engine's intake to be burned.
So it recycles those gases. Exactly. It prevents them from just venting into the atmosphere, which is bad for emissions, and it also prevents that pressure buildup in the crankcase that can push oil out past seals.
What goes wrong with it?
The PCV valve itself can get clogged with sludge or carbon, or it can get stuck open or closed. A clogged or stuck closed valve leads to pressure buildup, oil leaks, maybe rough idle. A stuck open valve can cause a vacuum leak, leading to a lean condition, rough idle, maybe even a whistling noise. Simple part, but important function.
Okay. How about the exhaust system? More than just a pipe, right?
Much more. The exhaust system obviously carries the hot exhaust gases away from the engine and out the back of the car safely. But it also houses critical emissions components. The catalytic converter is the main one. It uses precious metals like platinum and rhodium to convert harmful pollutants like carbon monoxide and hydrocarbons into less harmful substances like CO2 and water.
That's the expensive part if it fails, right?
It can be, yeah. And you also have O2 sensors located in the exhaust, both before and after the catalytic converter, monitoring its efficiency. Regular inspection of the exhaust is important, looking for leaks, rust, damage, or signs of restriction. A clogged catalytic converter, for example, can create huge back pressure and severely choke engine power.
Right. What about fuel vapors? I hear about EVP systems.
Ah, yes, the Evaporative Emissions Control, EVV system. Its whole job is to capture gasoline vapors that naturally evaporate from the fuel tank and fuel lines, preventing them from escaping into the atmosphere. Gasoline is volatile, it wants to evaporate.
So where do the vapors go?
They're collected in a charcoal canister, which is like a storage tank filled with activated carbon that absorbs the vapors. Then, under specific conditions when the engine is running, a purge valve opens, and the engine vacuum draws those stored vapors from the canister into the engine to be burned along with the regular fuel. There's also a vent valve that controls airflow into the canister.
What kind of problems happen here?
EVAP system issues are actually a very common reason for the check engine light to come on. It could be a leak somewhere in the lines, a faulty purge or vent valve, or even something as simple as forgetting to tighten your gas cap properly after refueling.
The gas cap. Really?
Absolutely. A loose gas cap creates a leak in the system detects it during its self-test, and boom, check engine light. Always tighten it till it clicks.
Good to know. Okay, one more thing for diesel owners. DEF fluid.
Right, diesel exhaust fluid, DEF. This is crucial for modern diesel vehicles equipped with selective catalytic reduction SCR systems. SCR is a technology designed to drastically reduce harmful nitrogen oxide, alcavius, emissions from diesel exhaust.
How does DPF?
DEF is a non-toxic solution, mostly urea and water. It's injected into the hot exhaust stream before the SCR catalyst. The heat breaks the DEF down into ammonia, and the ammonia then reacts with the NOx inside the catalyst, converting it into harmless nitrogen gas and water vapor.
So you have to keep the DEF tank filled.
Yes. Maintaining the proper DEF level is absolutely crucial. If the level gets too low, you'll get a warning light on the dash, and eventually the vehicle's computer will significantly reduce engine power, sometimes called limp mode, to force you to refill it. It's an essential part of meeting modern diesel emissions standards. ####BHIP automatic transmission transaxle. 8% of G1 test 4 questions.
All right, great info on engines. Let's move on from the power source and talk about how that power gets delivered seamlessly to the wheels in most cars today. Automatic transmissions and transaxles. What are the key things that drivers should be aware of here? This is only about 8% of the G1 test, just 4 questions, so maybe less complex.
Well, less complex in terms of the number of questions, maybe, but the system itself is incredibly complex. Automatic transmissions are these amazing pieces of engineering responsible for taking the engine's power and transmitting it to the drive wheels, all while automatically selecting the right gear ratio for smooth acceleration and cruising.
Okay, so what's the most critical element for keeping it healthy? Something I can actually check.
Without a doubt, the transmission fluid. It's the lifeblood of an automatic transmission. It performs multiple, absolutely vital functions.
Like what? Just lubrication.
Lubrication is huge, yes, for all those intricate moving parts, clutches, gears, bearings. But it also acts as a hydraulic fluid, transmitting pressure to engage clutches and shift gears. And it's crucial for cooling. Automatic transmissions generate a lot of heat, and the fluid carries that heat away to a cooler. So lubrication, hydraulic pressure, and cooling. All from the fluid.
Okay, so checking the fluid is key. How do I know if my transmission fluid is healthy or if there's a problem brewing? What I'm looking for.
Inspection is definitely key. You should check your transmission fluid level and condition periodically. Now, the procedure varies. Some cars have dipsticks like the engine oil. Others have sealed units that need a technician. Check your owner's manual for the correct procedure and, importantly, whether the engine should be hot or cold, running or off.
And what visual cues signal trouble?
You're looking at the color and smell. Healthy fluid is usually bright red and doesn't have a strong odor. If the fluid looks dark brown or black, or if it smells burnt toast, that's a sign of overheating or excessive wear.
Burnt smells bad. What else?
If the fluid looks milky or pinkish and frothy, that usually indicates coolant contamination. There's likely a leak in the transmission cooler inside the radiator, allowing engine coolant to mix with the transmission fluid. That's very serious and needs immediate attention, as coolant destroys clutch materials.
Milky fluid means coolant. Got it. Anything else?
Yeah, sometimes when the fluid is changed, the technician will inspect the bottom of the transmission pan or check the magnet that's often in there. If they find significant amounts of metallic particles or debris, that's a clear signal of excessive internal wear. Clutches, bands, gears grinding themselves down. Not a good sign.
Okay, so fluid checks are important. What's the standard maintenance beyond just checking?
Regular maintenance typically involves draining the old fluid and refilling with fresh fluid of the correct type, and usually replacing the transmission filter at the manufacturer's recommended intervals. These intervals vary quite a bit, so check your manual.
And they check the pan then?
Yeah. When they drop the pan to change the filter, that's when they inspect it for that debris we mentioned. It gives crucial clues about the transmission's internal health. Also, related to the whole powertrain are the powertrain mounts or engine transmission mounts.
What are those do?
These are essentially rubber or hydraulic shock absorbers that support the weight of the engine and transmission and isolate their vibrations from the car's body. They keep everything aligned and smooth.
How do I know if they're failing?
If the mounts wear out or break, you'll likely notice things like excessive engine movement when you accelerate or shift gears, maybe clunking noises or unusual vibrations felt inside the cabin. It can feel like the whole engine is shifting around under the hood. #tag train axles, 10% of G1 test 6 questions.
Okay, that covers automatics. Now, for those drivers who, like me sometimes, prefer having that third pedal and rowing through the gears themselves, let's talk manual drivetrains and axles. How do these systems connect the power? This is about 10% of the test, 6 questions.
Right. So in a manual transmission vehicle, these systems are responsible for transferring the power from the transmission, which you control with the shifter, out to the wheels. The clutch system is obviously fundamental here.
That's what lets you shift gears smoothly.
Right,
Yeah.
exactly. It allows you to momentarily disconnect the engine's power from the transmission so you can select the next gear without grinding. Most modern manual cars use a hydraulic clutch system.
How does that work?
It's similar in principle to your brakes. You push the clutch pedal, which moves a piston in the clutch master cylinder. This sends hydraulic fluid through a line to the clutch slave cylinder, which then pushes a lever or fork that engages the release bearing, disengaging the clutch disc from the flywheel.
So fluid is important here, too.
Very important. You need to maintain the proper fluid level and condition in the clutch master cylinder reservoir. If the fluid looks dark, dirty, or low, it can cause problems with clutch operation difficulty shifting. Maybe the pedal feels spongy or goes to the floor.
Okay, and what connects my shifter inside the car to the actual transmission?
That's the shift linkage. It can be a series of rods, levers, or sometimes cables. It physically connects the movement of your gear shifter to the shifting forks inside the transmission, allowing you to select first, second, third gear, and so on.
What goes wrong with the linkage?
Over time, bushings in the linkage can wear out, making the shifter feel loose, sloppy, or vague. Sometimes it might become difficult to get into certain gears if the linkage is misadjusted or bent. You might feel excessive play in the shifter knob.
Okay, now how does the power get from the transmission out to the actual wheels, especially considering the wheels need to move up and down with the suspension in turn?
That's where drive shafts and hash shafts come into play. In a rear-wheel drive car, you typically have a long drive shaft connecting the transmission to the rear differential. In a front-wheel drive car, you have two shorter shafts, often called hash shafts or drive axles, connecting the transaxle directly to the front wheels.
They have those flexible joints, right?
Exactly. Especially on front-wheel drive cars and also on vehicles with independent rear suspension, you have CV joints, which stand for constant velocity joints. These are critical. They're marvels of engineering, designed to transmit power smoothly through a wide range of angles as the wheels turn for steering and move up and down with the suspension, all without any change in rotational speed or vibration.
What are the common problems with CV joints? What should I listen for?
The most common symptom of a failing CV joint is noise, usually a distinct popping, clicking, or sometimes clunking sound, especially when you're accelerating while turning sharply, like pulling out of a parking spot.
Popping or clicking on turns.
Yeah.
Got it.
Right. And visually, the most important thing to check, or have checked, are the protective rubber boots that cover the CV joints. These boots hold lubricating grease in and keep dirt and water out.
What happens if a boot tears?
If a boot tears or cracks, the grease slings out and dirt and moisture get in. This quickly contaminates the joint, washes away lubrication, and leads to rapid wear and failure of the joint itself. You might see grease splattered inside your wheel well. Catching a torn boot early and replacing just the boot is relatively inexpensive. Letting it go until the joint starts making noise usually means replacing the entire half-shaft assembly, which is much more costly.
So check the boots periodically. Good tip.
Mm-hmm.
Now, what actually allows the wheels themselves to spin freely with minimal friction?
That's the job of the wheel bearings. Their whole purpose is to allow the wheels to rotate smoothly around the axle, spindle, or hub with very little friction.
Are there different kinds?
Yeah. Common types include ball bearings, roller bearings, and increasingly sealed unitized hub bearings, which are non-serviceable assemblies. But you don't really need to worry about the types. What's important is recognizing the symptoms of failure.
Which are?
Noise is the primary symptom, usually a grinding, humming, or roaring sound that often changes pitch or intensity with vehicle speed, or sometimes when turning. It might sound like you're driving on knobby mud tires even when you're not. Another symptom can be looseness or play in the wheel if you were to jack the car up and try to wiggle the wheel top to bottom or side to side. Worn bearings are a safety issue as they can eventually seize or cause the wheel to wobble.
Grinding or humming noise that changes with speed. Okay. What about the back axle, the differential?
Right, the differentials and axles. The differential is that gear housing, usually in the center of the drive axle, rear axle on RWD, often integrated into the transaxle on FWD. Its main function is clever. It allows the drive wheels on the same axle to rotate at different speeds when you go around a corner.
Why is that necessary?
Think about making a turn. The outside wheel has to travel a longer distance than the inside wheel in the same amount of time, so it needs to spin faster. The differential makes this possible, preventing wheel hop and tire scrubbing during turns.
Does it need maintenance?
Yes. Like the engine and transmission, the differential contains gear oil that needs to be checked and sometimes changed according to the manufacturer's schedule. Keeping the fluid level correct and the fluid clean is important for the longevity of the gears inside.
Okay. And briefly, what about 4WD and AWD systems?
Right. Four-wheel drive, 4WD, and all-wheel drive AWD systems are designed to send power to all four wheels for improved traction, especially in slippery conditions like snow, mud, or rain. 4WD systems often have a separate transfer case and allow the driver to select between 2WD and 4WD modes. AWD systems are typically always active, automatically distributing power between front and rear wheels as needed.
What kind of issues do they have?
Common issues can include noise, vibration, or harshness, often abbreviated NVH, coming from components like the transfer case, drive shafts, or differentials. Sometimes problems arise with the system engaging or disengaging properly. These systems add complexity, so maintenance, like changing transfer case fluid, is important. ###DR suspension and steering, 20% of G1 test 11 questions.
All right, let's move on to a system pair that's all about comfort and control, and obviously safety too. Suspension and steering. This is a pretty hefty chunk of the G1 test, 20%, about 11 questions. Which makes sense, right? They impact so much about how the car feels and handles. What's the core job here?
Yeah, it's a critical pairing. They have a vital dual role. The suspension system's primary job is to absorb road shocks and imperfections, isolating the car's body from bumps and vibrations for a smooth, comfortable ride. It also works to keep the tires firmly planted on the road surface for maximum grip.
And steering.
The steering system provides precise control over the vehicle's direction, allowing you to guide the car accurately and maintain stability. They really work hand in hand to deliver both comfort and confident handling.
Okay, before we dive into the components, you mentioned something earlier about safety systems when working near these parts.
Yes, absolutely critical. The Supplemental Restraint System, or SRS, this is your airbags, seatbelt pretensioners, the whole safety net. It's woven into areas around the steering column, dashboard, sometimes even seats. It is crucially important for anyone, professional or DIYer, to know how to properly disable the SRS system before doing any work on or near related components like the steering wheel, column, or certain dashboard parts. Accidental deployment can cause serious injury.
Okay, so SRS is serious business. Always follow safety procedures or leave it to the pros.
Got it.
Now, how about making it easy to turn that steering wheel? Especially on heavier cars, it used to be a real workout.
Right. That's power steering. It takes the wrestling match out of steering. Modern systems dramatically reduce the effort needed to turn the wheels, especially at low speeds like parking.
Are there different types?
Yeah, two main types commonly found today. Traditional hydraulic power steering uses fluid pressurized by an engine-driven pump to assist your steering effort. Newer systems often use electronic power steering, EPS, which uses an electric motor directly assisting the steering rack or column, eliminating the need for hydraulic fluid and pumps.
What problems might I notice with power steering?
With hydraulic systems, the most common issues are fluid leaks. You might see reddish or amber fluid dripping, or notice the fluid level in the reservoir is low. Check the fluid color. If it looks dark or foamy, that's not good. You might also hear noises like a whining or groaning sound, especially when turning the wheel, which often indicates low fluid or a failing pump. And of course, the main symptom of failure is increased steering effort. It suddenly becomes much harder to turn the wheel. EPS systems can have electrical issues, sensor failures, or motor problems, often triggering a warning light on the dash.
So checking the fluid level on hydraulic systems is good preventative maintenance.
Definitely. Keep an eye on the reservoir level and condition if your car has that type.
Okay, so the power steering helps turn it, but what actually connects my steering wheel input down to the wheels on the road? What makes them turn left and right?
That's the job of the steering linkage. It's the mechanical connection. Think of it as a series of rods, arms, and joints that transmit the rotational motion from your steering wheel via the steering gear or rack out to the steering buckles that the wheels are attached to.
What are the key parts?
Common components include tie rods, inner and outer, which are adjustable rods that connect the steering gear to the steering arms on the knuckles. On some systems, you might also have a pitman arm and an idler arm as part of the linkage.
How do I know if there's wear in the linkage? What should I look or listen for?
The main things to look for during inspection are looseness or excessive play in the joints, worn bushings, or damage. As a driver, you might notice symptoms like excessive play or looseness in the steering wheel, meaning you can turn the wheel a fair bit before the car actually starts to turn. You might also hear noises like clunking, popping, or rattling sounds, especially when turning or going over bumps. Worn tie rod ends are a very common cause of these symptoms and can also affect wheel alignment.
Clunking or looseness means check the linkage. Got it. Now, for that smooth ride, soaking up bumps and keeping the tires on the road, that's all suspension, right?
That's the suspension's domain. Its job is to manage the relationship between the wheels and the car body. It uses a combination of springs to support the vehicle's weight and absorb large bumps, and shock absorbers, or struts, which combine the spring and shock into one unit, common on front suspensions, to control the bouncing motion of the springs.
So springs handle the bumps, shocks handle the bounce.
Essentially, yes. Without shocks, the car would just keep bouncing up and down after hitting a bump, like an old horse-drawn carriage. Shocks, or struts, dampen that oscillation, keeping the tires firmly in contact with the road for better control and braking.
What are the other important suspension parts?
You also have control arms, which locate the wheel assembly and allow it to move up and down. Ball joints are crucial pivot points, like your shoulder or hip joint, allowing the wheel to steer and move with the suspension. And various bushings, usually made of rubber or polyurethane, are used at connection points to absorb vibration and allow controlled movement while minimizing noise.
What are the symptoms if these parts wear out? How would I know my suspension needs attention?
Several telltale signs. Noise is a big one: clunking, rattling, squeaking, or groaning sounds, especially when going over bumps, turning, or braking. You might notice uneven tire wear, as worn suspension parts can affect alignment. Poor handling is another symptom. Maybe the car feels unstable, wanders, leans excessively in corners, or feels overly bouncy or floaty. And visually, you might see fluid leaking from a shock absorber or strut body, which means it's lost its damping ability and needs replacement.
Bouncy, noisy, or leaky means get the suspension checked. Okay. And all these steering and suspension parts need to be pointing the wheels in the right direction, which brings us to wheel alignment. Why is that so critical? It seems like something shops always try to sell.
It is critical, and for good reason, not just an upsell. Proper wheel alignment is absolutely essential for several key things: preventing rapid and uneven tire wear, saving you money on tires; ensuring proper vehicle handling and stability, making the car safer and easier to drive; and even contributing to optimal fuel economy, because crooked wheels create drag.
Okay, so tire wear, handling, fuel economy, makes sense. I hear terms like camber, caster, toe. What do those actually mean?
Those are the three main alignment angles technicians adjust. Let's break them down simply. Camber is the inward or outward tilt of the top of the wheel when you look at it from the front of the car. Think of your knees bending slightly in or out. Too much negative camber, top tilted in, was the inside edge of the tire. Too much positive camber, top tilted out, where's the outside edge?
Okay, camber is the vertical tilt.
Right. Caster is the forward or backward tilt of the steering axis when viewed from the side of the car. Think of the front forks on a bicycle or motorcycle. They're angled forward. That's caster. Positive caster helps with steering stability, making the car want to go straight, and helps the steering wheel return to center after a turn. It doesn't typically cause tire wear directly, but affects handling feel.
Caster is the forward-backward tilt for stability.
Got it.
And toe.
Toe is the direction the wheels are pointing relative to each other, like looking down at your feet. Toe in means the front edges of the tires are slightly closer together than the rear edges. Toe out means the front edges are farther apart. Incorrect toe is the biggest cause of rapid tire wear, often causing a feathered or sawtooth pattern across the tread. Even being slightly off can scrub rubber off quickly.
Toe is the inward-outward angle, and it eats tires fast. Okay, that helps understand why alignment matters.
Exactly. It's about making sure all four wheels are pointed in precisely the right direction, relative to each other and to the vehicle itself, to minimize wear and maximize control.
And that brings us to the tires themselves, literally the only part of the car touching the road. What should we be looking for there?
Wheels and tires are incredibly important. Your life literally rides on them. We just talked about alignment causing wear, but learning to read tire wear patterns can tell you a lot.
Like what?
Like we said, wear on just the inside or outside edges usually points to a camber issue. Feathering or sawtoothing across the tread blocks often indicates a toe problem. Scalloped or cupped wear, where dips are worn into the tread, can indicate worn shock struts or wheel imbalance. Wear right in the center of the tread suggests overinflation. Wear on both outer shoulders suggests underinflation. Periodically running your hand over the tread carefully and looking closely can give you early warnings.
So the tires can diagnose other problems. Cool. What's the most basic tire care?
Tire pressure. Absolutely fundamental. Always maintain the pressure recommended on the vehicle's door placard or sticker, usually found on the driver's side door jamb or door edge. Not the pressure listed on the tire sidewall itself. That's the maximum pressure the tire can hold, not the recommended pressure for your specific vehicle.
Why is the placard pressure so important?
Because the vehicle manufacturer determines that pressure based on the vehicle's weight and suspension design to provide the best balance of handling, ride comfort, tire life, and load carrying capacity. Underinflation causes overheating, excessive shoulder wear, poor handling, and bad fuel economy. Overinflation causes a harsh ride, center tread wear, and reduced traction. Check your pressure regularly, at least once a month, and always when the tires are cold.
Okay, placard pressure, check monthly when cold. What about that little tire light on the dash? TPMS.
Right, the Tire Pressure Monitoring System, TPMS, mandated on new cars in the U.S. since 2007. Its job is to alert you with a warning light if one or more of your tires become significantly underinflated, usually 25% below the recommended pressure.
How does it know?
There are two main types. Direct TPMS uses battery-powered sensors inside each wheel, often part of the valve stem, that directly measure the pressure and transmit that info wirelessly to the car's computer. Indirect TPMS doesn't use pressure sensors. Instead, it uses the existing anti-lock brake system, ABS, wheel speed sensors. It looks for differences in the rotational speed of the wheels. An underinflated tire has a slightly smaller diameter and spins faster than the others.
Does it matter which type I have?
Not really to the driver. The warning light functions the same. The main thing is if that TPMS light comes on, don't ignore it. Pull over safely as soon as possible and check the pressure in all four tires and the spare if it's monitored. It's a critical safety warning. Hashtag e-brakes. 15% of G1 test 8 questions.
Okay, speaking of critical safety systems, let's talk about the big one. Brakes, probably the single most important safety feature on your car, accounts for a solid 15% of the G1 test, about 8 questions. Makes sense. How do they actually work to stop potentially thousands of pounds of moving metal?
It's an amazing system, really. The foundation of most modern car braking systems is hydraulics. It all starts when you push the brake pedal.
Okay, put on the pedal.
That pedal pushes a rod into the master cylinder. The master cylinder is basically the heart of the hydraulic system. It contains pistons and seals within reservoirs filled with brake fluid. When you push the pedal, these pistons move and convert your mechanical foot pressure into hydraulic pressure within the brake lines.
So it magnifies the force.
Greatly magnifies it using hydraulic principles. This high-pressure brake fluid is then forced through a network of strong steel brake lines and flexible rubber hoses that run out to each wheel.
And what happens at the wheels?
At each wheel, the hydraulic pressure acts on either a wheel cylinder in drum brakes or a brake caliper in disc brakes. These components then use that pressure to force friction materials, brake shoes, or brake pads against a rotating surface, the brake drum or brake rotor attached to the wheel. That friction is what slows and stops the car.
Friction creates heat, right?
Yeah.
Brakes must get really hot.
Incredibly hot. That's a key challenge in brake design, dissipating all that heat generated from converting motion energy into heat energy.
Now, you mentioned brake fluid. I know there are different types like DOT3, DOT4. Does it matter which one you use? And why do mechanics always talk about flushing it?
Yes, it matters immensely. You should always use the specific type of brake fluid recommended by your vehicle manufacturer. Check your owner's manual or the master cylinder cap. The most common types, DOT3 and DOT4, are glycol-based fluids. The key thing to know about them is that they are hygroscopic.
Hygro what?
Hygroscopic, it means they readily absorb water moisture directly from the surrounding air, even through microscopic pores in brake hoses. Think of it like a sponge soaking up humidity over time.
Why is absorbed water bad? I thought water doesn't compress.
Water itself doesn't compress easily, that's true. But water boils at a much, much lower temperature, 212 degrees F or 100 degrees C, than fresh brake fluid. which can be over 400 degrees or 200 degrees C. So if your brake fluid becomes contaminated with too much water, under heavy or prolonged braking, like going down a long mountain past the heat generated, can actually boil that absorbed water within the brake lines or calipers.
What happens when the water boils?
It turns into steam, into water vapor. And unlike liquid fluid, steam is highly compressible. So when you step on the brake pedal, instead of instantly transmitting pressure, you're compressing these steam bubbles first. This leads to a terrifyingly spongy or soft brake pedal that might sink almost to the floor and dramatically reduced stopping power. It's called vapor lock.
Wow. Okay, that's why they recommend flushing it.
Exactly. Regular brake fluid flushing replaces the old moisture-contaminated fluid with fresh dry fluid, restoring the high boiling point and preventing vapor lock. It also removes contaminants and helps prevent internal corrosion of expensive brake components like the master cylinder, calipers, and ABS unit. It's critical preventative maintenance.
And what if air gets in the lines somehow, like during a repair?
Air in the lines also causes a spongy pedal because air is compressible too. That's why bleeding the brakes is necessary anytime the hydraulic system is opened up, like when replacing a caliper or brake line. Bleeding forces the air bubbles out, leaving only solid, incompressible fluid.
Makes sense. Now, what about all those different brake warning lights on the dashboard? Sometimes it feels like there's a whole constellation of them.
Yeah, they provide crucial status updates. A primary red brake warning light, often looks like, or brake, can indicate several things. It might mean your parking brake is still engaged, check that first, but it could also mean the brake fluid level in the master cylinder is low, or there's a potentially serious pressure loss or imbalance in the main hydraulic system. A red light needs immediate attention.
Red means stop and check. What about yellow or orange lights?
A yellow or orange light, often saying ABS, indicates an issue specifically with the anti-lock braking system.
What does ABS actually do again? I know it helps prevent skidding.
Precisely. Its job is to prevent the wheels from locking up solid during hard braking or on slippery surfaces. Locked wheels lose steering control and generally increase stopping distance. ABS works by constantly monitoring the speed of each wheel using wheel speed sensors. If it detects one wheel is about to lock up, i.e. decelerating much faster than the others, the ABS control module commands hydraulic valves to rapidly pulse the brake pressure to that specific wheel, sometimes many times per second.
So it pumps the brakes for you, but way faster.
Exactly. You'll often feel this rapid pulsing through the brake pedal during an ABS stop and might hear a buzzing or grinding noise. That's normal. It means the system is working. It allows you to maintain steering control while braking hard, which can be crucial for avoiding an obstacle.
So if the ABS light is on,
If the ABS light is on, it means the anti-lock function is disabled due to a fault, like a bad sensor or module. Your regular brakes should still work normally, but you won't have the anti-lock assist in a panic start. You should still get it checked out promptly.
Okay. Now, you mentioned drum brakes and disc brakes earlier. What's the real difference, and why do many cars have discs in front and drums in back?
Good question. Disc brakes generally offer superior stopping power, better heat dissipation, they're more exposed to air, and perform better in wet conditions compared to drum brakes. That's why they're almost always used on the front wheels, which handle the majority, often 60–70% of the braking load, due to weight transfer during deceleration.
So what are the parts of a disc brake?
Key components are the flat rotating rotor, or disc, that's attached to the wheel hub, the caliper, which houses the brake pads and pistons, and the brake pads themselves, which are the friction material. When you apply the brakes, hydraulic pressure pushes pistons inside the caliper, which clamp the pads against both sides of the spinning rotor, creating friction.
An inspection involves checking the pads and rotors.
Yep. You check the pad thickness for wear, and you inspect the rotor surface for damage like deep scoring, cracks, or excessive rust. You also measure the rotor's thickness to ensure it's above the minimum safe limit and check its runout, any side-to-side wobble as it rotates. Excessive runout causes that pulsing sensation in the brake pedal. Rotors often need resurfacing, machining them smooth again, or replacement if they're worn below minimum thickness, warped, have excessive runout, or badly scored.
Okay. And drum brakes. Less common now, but still around on rear axles.
Right. Drum brakes work differently. They consist of a hollow, rotating drum attached to the wheel hub, curved brake shoes with friction lining inside the drum, and wheel cylinders that push the shoes outward against the inner surface of the drum when you apply the brakes.
How are they inspected?
Inspection involves removing the drum to check the shoe lining thickness for wear, looking for any scoring or heat damage on the inside surface of the drum, and checking the wheel cylinders for any fluid leaks. Drum brakes also usually require periodic adjustment to maintain the correct clearance between the shoes and the drum as the linings wear. Many have automatic adjusters, but they can sometimes stick.
Got it. One last thing on brakes, that feeling of easy braking. I know my parents' old car, you really had to stand on the pedal. What makes modern brakes feel so effortless?
That's the magic of power assist units, also known as brake boosters. These units are installed between the brake pedal and the master cylinder, and their sole purpose is to multiply the force you apply with your foot, making braking much easier and requiring less leg effort.
How does he do that?
The most common type is a vacuum booster. It uses engine vacuum, or sometimes a separate vacuum pump, acting on a large diaphragm inside the booster canister to add force to the pushrod going into the master cylinder. Some heavier vehicles, or those with limited engine vacuum, like diesels or turbocharged engines, might use a hydroboost system, which uses hydraulic pressure generated by the power steering pump to provide the assist.
What happens if the booster fails?
The primary symptom is suddenly needing much more physical effort to push the brake pedal. It feels very hard or dead. The brakes will still function, the direct mechanical link is still there, but you lose that power assist, making it feel like you have to stand on the pedal to get the car stopped. It can be quite alarming if it happens unexpectedly. It's a very clear sign the booster system needs checking. ###F electrical. 8% of G1 tests 6 questions.
Okay, we've covered a lot of mechanical and hydraulic systems. But in today's cars, pretty much everything involves electricity, doesn't it? From starting the engine to the radio to the windows, it really is the vehicle's nervous system. What are the electrical basics we should grasp? This section is about 8% of the test, 6 questions.
You're absolutely right. Electrical components are everywhere, and they're becoming increasingly complex with modern features. When it comes to diagnosing electrical issues, the fundamental tool for any technician is the digital multimeter, or DMM.
The DMM, what does that actually measure?
A DMM is versatile. It measures 3 key electrical properties. Voltage, volts, which you can think of as the electrical pressure or potential difference in a circuit. Current, amps or amperes, which is the rate of electrical flow, like the volume of water flowing through a pipe. And resistance, ohms, which is how much a component or wire opposes the flow of electricity, like friction in the pipe.
Volts, amps, ohms. Okay, how are they used in diagnostics?
Understanding how to use a DMM to test circuits is fundamental. You might check for voltage to see if power is reaching a component, measure resistance to check if a switch or wire is good, low resistance, or broken, infinite resistance, or sometimes measure current draw to see if a component is using too much power. One very common and useful diagnostic technique is checking for voltage drop.
Voltage drop, what's that?
Voltage drop testing helps find unwanted resistance in a circuit that shouldn't be there. Think of it like checking for a kink or blockage in a garden hose. You measure the voltage difference between 2 points while the circuit is operating. A significant voltage drop across a connection, switch, or section of wire indicates high resistance, maybe a loose connection, corrosion, or a frayed wire that's hindering current flow and potentially causing a component to malfunction. It's a great way to pinpoint problems without just replacing parts.
Okay, finding unwanted resistance, that makes sense. Now, where does all this electrical power actually come from in the car, and how is it managed?
It starts with the battery. The battery's primary role is to provide the large burst of electrical energy needed to crank the starter motor and get the engine running. It also acts as a voltage stabilizer and powers all the vehicle's electrical accessories when the engine isn't running, like your interior lights or radio.
How do you know if your battery is good?
Technicians use specialized testers to check a battery's voltage. A fully charged car battery should be around 12.6 volts when resting, and its cold cranking amps, CCA capacity, which is its ability to deliver power in cold temperatures. For you, the driver, the most important maintenance is keeping the battery terminals clean and tight. Corrosion buildup looks like white or blue fuzzy stuff and acts as an insulator, preventing good electrical contact and potentially causing starting problems or charging issues.
Okay, so battery starts it. What keeps it going?
Once the engine is running, the charging system takes over. The key component here is the alternator. The alternator is essentially an electrical generator driven by the engine's serpentine belt. Its job is to produce all the electrical power needed to run everything on the vehicle lights, ignition, fuel pump, computers, accessories, and simultaneously recharge the battery.
So the alternator keeps the battery topped up.
Exactly. And working hand in hand with the alternator is the voltage regulator. Its crucial job is to control the alternator's output, maintaining a relatively constant system voltage, usually around 13.5 to 14.5 volts when the engine is running, regardless of engine speed or electrical load. This prevents overcharging the battery and protects sensitive electronic components from damaging voltage spikes. If the regulator fails, you might get undercharging, leading to a dead battery, or overcharging, which can boil the battery fluid and damage electronics.
Okay, battery stores power, starter cranks, alternator makes power while running, regulator controls it. Got the basics. What about other common electrical things like lights and the dashboard display?
Lighting systems are obviously critical for safety and visibility. Headlights come in various technologies. Now, older halogen bulbs, brighter HID, high-intensity discharge systems that use an arc, and modern, efficient LED, light-emitting diode, headlights. Regardless of type, proper headlight aim is crucial, ensuring they illuminate the road effectively without blinding oncoming drivers. Common issues are simple burned-out bulbs, dimness, which could be aging bulbs, corroded connections, or sometimes an alternator issue, or problems with switches or relays.
And the dashboard, all those gauges and lights.
That's the instrumentation. It's your primary interface for understanding the vehicle's status. You have gauges that provide continuous readings like the fuel level gauge, engine temperature gauge, tachometer, engine RPM, and speedometer. And you have warning lights, sometimes called idiot lights, though that's a bit harsh, that alert you to specific problems. The check engine light, oil pressure warning light, brake warning light, battery charging system light, TPMS light, and so on. Learning what each gauge normally reads and what each warning light means is a fundamental part of being an informed and safe driver. They provide vital, real-time feedback. #, G heating, ventilation and air conditioning, HVAC. 7% of G1 Test 4 questions.
All right, last major system area from the G1 guide, and one we definitely appreciate for comfort, especially during extreme weather. HVAC heating, ventilation, and air conditioning. Only about 7% of the test, 4 questions, but essential for surviving summer heat or winter cold. What's the main job here?
The HVAC system is all about controlling the climate inside your car's cabin. Its role is to maintain a comfortable temperature, manage humidity levels, provide fresh air ventilation, and filter the air coming into the cabin. It keeps you comfortable and helps with visibility by defrosting or defogging windows.
Okay, the cooling part, the AC, uses that special refrigerant chemical, right?
Correct. The key to the air conditioning side is the refrigerant. It's a specialized chemical that has the ability to easily change state between a liquid and a gas, absorbing a large amount of heat in the process. Common types used over the years include the old R12, phased out due to ozone damage, the widely used R134A, and the newer, more environmentally friendly R1244 found in most brand new cars.
Do I need to worry about which type my car uses?
Not necessarily for driving, but it's critical for servicing. You can't mix refrigerants. And more importantly, there are strict EPA regulations regarding the handling, recovery, and recycling of all automotive refrigerants due to their potential environmental impact, global warming potential.
So definitely not a DIY recharge with those cans from the auto parts store.
It's strongly discouraged and often illegal depending on the refrigerant and location. Servicing AC systems requires specialized equipment to properly recover any existing refrigerant, evacuate the system, remove air and moisture, check for leaks, and precisely recharge with the correct amount and type of refrigerant and oil. Mishandling refrigerant can be harmful to you and the environment. If your AC isn't blowing cold, it really is a job for a properly equipped and certified professional.
Good advice. Okay, so refrigerant is the magic ingredient for cooling. What are the main hardware components that make the whole HVAC system work?
There are several core components working together. For the AC side, you have the compressor, which is belt-driven by the engine and acts like a pump, compressing the refrigerant gas and circulating it through the system. The condenser, usually located in front of the radiator, is where the hot, high-pressure refrigerant gas releases its heat to the outside air and condenses back into a liquid.
Okay, compressor pumps it, condenser cools it off.
Right. Then the high-pressure liquid refrigerant flows to an expansion valve or orifice tube, which meters its flow into the evaporator. The evaporator, typically located inside the dashboard behind the glove box, is where the magic of cooling happens. The refrigerant rapidly expands and evaporates back into a low-pressure gas, absorbing a tremendous amount of heat from the cabin air blowing across its fins in the process. That's what makes the air cold.
Evaporator makes the cold air. Got it. What about moving the air?
That's the job of the blower motor.
Yeah.
It's essentially a fan that pushes air through the evaporator for cooling, or the heater core for heating, and then directs it through the ducts to the vents in your dashboard floor or defrost outlets based on your control settings.
Okay. And I know there's a filter involved somewhere.
Yes, the cabin air filter. This is an often overlooked but important component. Its job is to filter the outside air before it gets blown into the cabin, removing dust, pollen, leaves, bugs, and other airborne pollutants.
Why is replacing it important?
Replacing it regularly, check your owner's manual, usually every 15,000 miles or so, or more often in dusty areas, is crucial for maintaining good air quality inside your car, which is especially important if you have allergies or respiratory issues. A clogged cabin air filter can also significantly restrict airflow from your vents, reducing the effectiveness of both your heating and cooling, and putting extra strain on the blower motor. If your airflow seems weak or smells musty or dusty, the cabin filter is the first thing to check.
Weak or musty air? Check cabin filter. Good tip. Is there anything else simple that can go wrong with HVAC?
One small but common issue is the evaporator housing drain. Remember how the evaporator gets cold and absorbs heat? It also condenses moisture out of the air, just like a cold glass on a humid day. This condensation drips down into a housing and is supposed to drain out through a tube underneath the car.
What happens if that drain gets clogged?
If the drain tube gets clogged with leaves, debris, or mold, the water can back up inside the housing. Eventually it overflows and you'll find water dripping onto the floor inside your car, usually on the passenger side footwell. It can lead to musty smells and wet carpets. It's often a simple fix just clearing the blockage, but it can be puzzling if you don't know what's causing the wet floor. Hashtag 3. Parts anxiety, just stop. The importance of quality components.
Listening to all this, diving deep into these complex systems, the engine, transmission, brakes, electrical, it's amazing how much is going on. But there's one piece of the puzzle that the average car owner like me might not think about much during a repair. But it feels absolutely crucial based on what you've said. I saw this ad slogan in the study guide material we looked at that just jumped out. Parts anxiety, just stop.
Ah, yes, the Motorcraft ad. That's a really powerful message, isn't it? It hits right at a core concern many people have when facing repairs. And it highlights something fundamental that often gets pushed aside in the quest for the cheapest possible fix, the actual quality of the replacement parts being used.
Right. The ad talks about using manufacturer-recommended parts, like Motorcraft for Ford and Lincoln vehicles. Why is that actually important? Aren't all replacement parts basically the same if they fit?
That's a common misconception, but no, they're definitely not all the same. The key point the ad makes is that parts like Motorcraft are not just generic aftermarket components made to roughly fit a bunch of different cars. They are specifically designed, engineered, and recommended by the original vehicle manufacturer, Ford, in this case. They were likely developed right alongside the vehicle itself during its design phase.
So it's about more than just fitting. It's about how they perform.
Precisely. It's about guaranteed fit and performance. That's the huge benefit, and it directly tackles that parts anxiety. These parts are engineered to meet the exact specifications, tolerances, and material standards set by the people who designed the entire car.
What does that mean in practical terms?
It means they integrate seamlessly with the rest of the vehicle's systems. They provide optimal performance, the braking distances the engineers intended, the fuel efficiency they calculated, the emissions levels they certified. And crucially, they're designed for long life reliability. They're built to last, reducing the likelihood of premature failure and the anxiety of wondering if that cheap part is going to leave you stranded next week.
Okay, so better fit, better performance, longer life. Makes sense. The ad also mentioned a huge inventory.
Yeah, something like 20,000 active parts available covering all the common maintenance and repair items like brakes, batteries, filters, belts, spark plugs, wiper blades, you name it. This wide availability means technicians using these parts can usually get the exact right part for your specific Ford or Lincoln quickly, minimizing downtime.
Okay, I see the benefits for the mechanic and the car's performance. But why does this really matter to me, the car owner footing the bill? It feels like maybe I could save money with a generic part, right?
This matters immensely to you because it directly impacts your vehicle's safety, reliability, and ultimately your wallet in the long run. Choosing generic or the absolute cheapest aftermarket part might seem like saving money up front. You might think, hey, this brake pad is half the price, why not?
Yeah, exactly.
But here's the potential downside. A poorly manufactured or slightly ill-fitting part, maybe made with substandard materials, can lead to several problems. It might fail prematurely, meaning you're back at the shop paying for the same repair again much sooner than you expected. It could negatively affect the performance of related components. Think about how a poorly performing sensor could impact fuel economy or engine smoothness. In some cases, especially with critical systems like brakes or steering, it could even compromise safety if the part doesn't perform exactly as the original engineers intended under stress.
I hadn't thought about it affecting other parts for safety.
Right. Using parts specifically designed and validated for your vehicle ensures that all those complex, interconnected systems we've been discussing can function together precisely as they were designed to. It maintains the vehicle's original performance characteristics, its safety standards, its fuel efficiency targets. It's really an aha moment about the unseen foundation of reliability. The components you choose to put into your car are a direct investment in its overall health, longevity, and your peace of mind behind the wheel. That initial saving on a cheap part can easily evaporate, and then some, with repeat repairs, inconvenience, or worse. It's about stopping that cycle of parts anxiety by choosing quality from the start.
Okay, wow. So we've covered the ASE G1 standard, toured all the major systems, even talked about the parts themselves. Bringing it all together, what does this deep dive really mean for you, the listener, the learner, the car owner, walking away from this conversation?
It feels like it's about more than just memorizing facts. It's got to be about practical empowerment, right? Turning that confusion we started with into actual confidence. Exactly. That's the ultimate goal. This knowledge isn't just trivia. It empowers you to make genuinely informed decisions when you're interacting with mechanics or dealing with car issues.
How so?
Well, for starters, you can ask better, more targeted questions. Instead of just saying, my car feels weird, you might say, I'm hearing a humming noise that gets louder with speed. Could it be a wheel bearing? Or you can ask, what specific diagnostic trouble codes did you find when you scanned it? Or, can you show me the condition of my brake fluid or pads?
So speaking their language a bit more.
Right. And you'll be better equipped to understand the diagnostic explanations the technician gives you. You can weigh the options more effectively and make truly informed choices about which repairs are essential right now, maybe for safety, versus which ones might be recommended preventative maintenance you could schedule later. You can differentiate, which can save you significant money and reduce that feeling of being pressured or upsold.
That makes sense. Does it also help with just day-to-day car ownership?
Yeah.
Being more proactive?
Absolutely. Knowing about common failure points and key inspection areas, like how to check your fluid levels and what to look for, learning to listen for specific abnormal noises like that spark knock or CV joint clicking, understanding what the different warning lights mean, it all allows for much more proactive maintenance and awareness.
Catching things early before they become big, extensive disasters.
Precisely. You might identify a potential problem early when it's still a relatively minor and inexpensive fix before it escalates into a costly breakdown or, worse, a safety hazard on the road. If you recognize the symptom of a failing water pump early, you might avoid the catastrophic engine damage from overheating. That kind of foresight, born from understanding, is like a superpower for car owners.
And something that really struck me throughout our discussion is just how connected everything is under the hood.
Right.
It's not just a collection of separate, isolated parts, is it?
Not at all. That's a crucial takeaway. The deep interconnectedness of vehicle systems. You have to constantly remind yourself that seemingly separate areas, the engine, the transmission, the electrical system, the cooling system, the brakes, they're all deeply intertwined and constantly communicating and affecting each other.
Can you give an example of that interconnectedness?
Sure. A simple example. A failing alternator electrical system won't properly charge the battery, which can then cause all sorts of seemingly unrelated electronic glitches, hard starting engine system, or even affect transmission shifting if the control module isn't getting stable voltage. Or think about how overheating cooling system can quickly damage transmission fluid and internal transmission parts. A problem rarely exists in total isolation.
So having that holistic view is key for really understanding car health.
It's absolutely crucial for effective problem solving, whether you're a technician or just an informed owner trying to describe symptoms accurately. It means that when one system starts sending out distress signals, it's always wise to consider its potential impact on or cause from other related systems.
Okay, to really make this practical and give everyone some solid takeaways, let's maybe revisit a few of those quick aha moments from the sample G1 questions you mentioned earlier, just to illustrate how this knowledge translates directly into real-world problem-solving thinking.
Great idea. These really crystallize the process.
Okay, what was the first one? Something about a radiator cap.
Right. Basic cooling system pressure test question. If a pressure test reveals the radiator cap is defective, what's the next step? The straightforward answer is replace the cap. Simple, direct diagnosis leads to a clear, logical action. Identify the faulty part, replace it. That's the core loop.
Okay, what about that internal coolant leak example?
Yeah, the engine leakage scenario. If an engine is losing coolant but has no visible external leaks, and the exhaust smells like sweet smoke or steam, what's the most likely cause? The answer points towards an internal leak, like a bad head gasket allowing coolant into the combustion chamber, or maybe the catalytic converter. This shows how you combine different, seemingly unrelated symptoms, coolant loss without puddles, plus an unusual exhaust smell to pinpoint a specific internal issue. You might not fix it yourself, but you know to tell your mechanic all those symptoms.
Right, describing the whole picture. Good point. And the brake fluid leak.
The question stated, a leaky master cylinder results in a soft brake pedal and low fluid level. What procedure is required? The correct procedure involves replacing the faulty master cylinder and then thoroughly bleeding the entire brake system to remove any air. This directly connects observable symptoms, soft pedal, low fluid, things you might notice, to a specific critical repair action.
And the multimeter question. Basic tool knowledge.
Yep. What setting on a multimeter, DMM, is used to check resistance? The answer is ohms, represented by the Greek letter omega A. Just a fundamental reminder that different electrical properties require different measurement settings on the essential diagnostic tool. It helps you understand the terminology when a tech says they need to ohm out a circuit.
Okay. And finally, that very specific clue from the AC system.
The HVAC fluid question. If the AC system's refrigerant oil appears milky when checked, what does it typically indicate? The answer is contamination by coolant. This is a perfect example of how a very specific visual cue, something a technician would look for during service, has a clear and immediate diagnostic implication, pointing directly towards an internal link between the cooling system and the AC system, likely in the evaporator or sometimes heater core.
Wow. So these examples really do drive home that point, don't they?
Yeah.
Understanding what the part does, what the symptom means, leads directly to understanding the why it's happening and how to approach fixing it. It arms you with knowledge. Hashtag tag outro. What an incredible journey we've taken today. Seriously, from the really intricate dance of pistons and valves inside the engine to decoding the subtle language of dashboard warning lights and even understanding why the quality of a simple replacement part actually matters. We've taken a genuinely deep dive into what keeps our vehicles running safely, reliably, and smoothly down the road. It's truly amazing how much complex technology is packed into the cars we often just take for granted.
It really is. And hopefully this deep dive has shown you, our listeners, that a vehicle isn't just, a metal box you fill with gas and point down the road. It's an incredibly complex, dynamic, interconnected system where every single component, big or small, plays a vital role in its overall performance, efficiency, and especially its safety.
Yeah.
Understanding even just the basics that we've covered today really does empower you. It helps you appreciate the phenomenal engineering involved. It enables you to make smarter, more confident decisions when it comes to maintenance and repairs, and maybe, just maybe, it helps reduce some of that parts anxiety or general repair anxiety we talked about.
Definitely. It's about shifting from feeling powerless to feeling prepared.
Exactly. Being a confident and prepared car owner, ready for whatever the road or your dashboard might throw your way.
So as you head back out on the road after listening to this, here's a final thought for you to mull over. What specific thing stands out to you the most about how interconnected even the seemingly simple systems in your car truly are? And how might this deep dive change your approach moving forward? Will you be listening more closely for certain noises now? Maybe checking your fluids or tire pressure more religiously? What part of your car are you most curious to learn even more about next?
Use this knowledge. Use it to be a more confident car owner, to ask better, more informed questions the next time you visit the repair shop. And perhaps it might even inspire you to take your own deeper dive into another specific automotive system that piques your curiosity. Keep learning, stay informed, drive safely, and enjoy the journey.